Let's look at the gas exchange process of internal combustion engines. As you all know, the gas exchange process includes induction process and the exhaust process. The induction process is in place to make sure we induce fresh charge into the cylinder as much as possible. And the exhaust process will ensure that the burned gases are removed from the system. Even though the power is produced during the combustion process or the expansion stroke of the engine, the intake and exhaust processes are also very much important for the performance of an engine, particularly the parameters like valve timing, valve lift, a proper coordination between intake and exhaust strokes are highly influential on the engine performance in general, its efficiency, as well as the emission control. Therefore, it is very much important for us to look at the gas exchange process in detail. Now, we looked at these components in the induction process earlier also. Now, as you can see here in this picture, the induction process starts from this point where the air is sucked in through the air filter, and then it is taken to the intake plenum via a air duct or pipe. And if it is a multi-cylinder engine, then this engine plenum would distribute this intake air into the different cylinders as required. And that distribution is done through the runners, and this entire system is called the intake manifold. Now, if it is a petrol engine, as we all know, there's a throttle valve before the air comes to the plenum. Now, this diagram schematically shows us these different components, how they are placed in the system. And this diagram is a real picture of an engine. Intake air duct or the pipe is not shown here, but this is the throttle body, and this is the plenum, and these are the runners, and they connect to the engine intake system. Now, earlier we looked at volumetric efficiency in little detail, but if you do a more comprehensive thermodynamic analysis considering ideal gas law, you can include several other parameters and write down a little more general statement or equation for the volumetric efficiency. So in terms of intake pressure, atmospheric pressure, compression ratio, exhaust pressure, and so forth. So all these parameters has a certain effect on the volumetric efficiency. And when it comes to designing of intake system, it is very much important for us to make sure that we volumetric efficiency will be maximized. On the other hand, if you look at the exhaust system, it also consists of several components. Exhaust manifold, as you can see here, which connects to the flange over here and to the catalytic converter. And there's an oxygen sensor down here. And then there is a silencer or muffler, and then the back box. So that is, again, a part of the silencer. So it's a two-stage process. Now, whenever you have various components connected to the exhaust system, as you can see here, of course, there's a pressure built up at each and every component. Accordingly, the efficiency of the exhaust process drops. Now, as you know, the nature of the fluid movement and the thermodynamics aspects are quite complex in an internal combustion engines. Therefore, to understand them accurately, we need to go for a complex three-dimensional models, mostly based on computational fluid dynamics techniques, which needs certain additional understanding about those mathematical techniques. However, just to understand what exactly going through in these processes, to a certain degree of accuracy, we could use simplified one-dimensional models. Now, for simplified analysis, we could assume that the flow in the intake and exhaust process is affected by two different scenarios. One is quasi-static effects, and the other one is the dynamic effects. Quasi-static effects and dynamic effects. The quasi-static effects are the things which change at a slow rate compared to the characteristic time scale of the system. So the characteristic time scale of the system is more or less the time per one cycle. So compared to that time scale, the things which are happening at a slower rate could be considered as quasi-static effects. Things happening rapidly, we could consider as dynamic effects. So the quasi-static effects are things happening at a slower rate, and dynamic effects are the things which are happening rapidly. Now, if you first look at the quasi-static effects, what are the quasi-static effects which influence on the intake system or exhaust system for that matter? One is the residual gases. So having the residual gases within the system could impact on the volumetric efficiency, charge composition, as well as the charge temperature. Usually, the residual gas, amount of residual gases depend on the compression ratio, exhaust gas temperature, and the intake and exhaust pressure ratio. Residual gases occupy the space or the volume that could have been occupied by the fresh air or fresh charge. Accordingly, the volumetric efficiency will be reduced due to residual gases. And on the other hand, if the exhaust gas temperature is high, then the intake gas will also be heated up. Accordingly, the density will be reduced. And on the other hand, mixing of exhaust gases or burn gases with the intake fresh air would change the intake air or charge composition. And another quasi-static effect that we observe in internal combustion engines is the evaporative cooling effect, particularly in the intake system. So if it is especially if it is a spark ignition engine, then we introduce fuel into the intake system, and the fuel will evaporate and cool down the intake air. Accordingly, there can be situations where the density is increased and the volumetric efficiency is increased. And the other quasi-static effect that we see is the displacement of air by the fuel and the water vapor. So the fuel only introduced in spark ignition engines, but water vapor is there in the ambient air all the time. So the volumetric efficiency is negatively affected by this displacement of fuel and water vapor. So this diagram shows the pressure ratio, intake air pressure ratio to intake system pressure ratio with the for the different type of fuels that we use at different equivalence ratios. So here, this side, it is a rich mixture, more fuel, and you can see the pressure of air drops with the increase of amount of fuel in the system. So that will negatively affect on the volumetric efficiency of the system. Now, if you look at the flow losses a little in detail, now we could consider two different scenarios here, wide open throttle condition, as well as partly closed throttle conditions. And this is the intake system. Air enters through the air filter, and there's a throttle valve, and this is an injection system where the fuel is injected over here. And this is the gasoline engine, the spark ignition engine. So the pressure variation you can see here on this side over here at different points of the intake system. So this is starting from this point, the length of the intake system starting from the air filter. So initially there is a drop of pressure at the air filter, and there will be a drop due to upstream manifold friction losses. And then there will be further losses at the throttle, depending upon the throttle position. So the losses will be minimum if it is wide open throttle, and maximum when it is idle conditions. And then there will be further losses at the valves, flow losses at the valves. We'll discuss those in detail. Accordingly, the pressure available just before the cylinder at the intake system would be somewhat less than the atmospheric pressure, that is the pressure before the air filter, air pressure before the air filter. So in diesel engines, of course, there is no throttle, therefore the throttle losses will be minimum. And if you look at this process on a PV diagram, so this is the pumping loop, and this is the exhaust process, and this is the intake process, and this box over here represent the throttling, so the throttling process. So the throttle losses are indicated over here, and intake flow losses are shown here, and exhaust flow losses are shown in this diagram over here. So those are the three different key losses that you can observe in an internal combustion engine. So if you look at the dynamic effects on the intake and exhaust system performance, one key parameter is the friction. Now, if you look at the frictional effects, the flow losses, I'm sure all of you know that the viscous friction force or the friction losses depend on the velocity of the flow. Accordingly, the pressure drop would be a constant, which is called the loss coefficient, the density, and the square of the velocity. Now, if you make this analysis quite simple by considering everything on average basis, and if you consider a simple system, m dot is the airflow into the system, and SP is the mean piston speed. On average basis, you could say whatever comes through the intake system would fill up the volume created by the piston as a result of its motion downwards during the intake stroke. So what comes, the mass comes into the system. If you assume density is constant, then mass comes into the system through the intake system is rho V into A, and what fills up the cylinder as a result of displaced volume is the mean piston speed into the cross-section area of the piston into the density. So if the density is constant, then you can say this quantity is proportional to this quantity. This is on average basis. Accordingly, the flow velocity will be proportional to the mean piston speed into the cross-section area of the piston divided by the cross-section area of the manifold runners. And usually this K, the loss coefficient, is proportional to the length of the manifold and divided by the diameter of the manifold runners. If you substitute these quantities into this relationship that we looked at earlier, so we will come to this relationship. And for a given intake system design, assuming that a fixed size of piston or the bore, we could say, and constant density, we could say delta P, or the pressure drop, is proportional to the square of the mean piston speed into L divided by d to power 5. d to power 5. If you look at this variation on an intake system, something like this, you can see the pressure drop drastically increases with the speed. Of course, it's a function of square of the speed. And also, when you consider 2 points like this, then the length of these 2 points also affect on the pressure drop. Accordingly, we can see the drop increases at a farthest point compared to the nearest point to the atmospheric conditions. You all know that the gas exchange process of an internal combustion engine is regulated by the valve timing, which is controlled by a mechanical cam. And the valve opening, which is not instantaneous, so it slowly opens and closes. The valve opening area provides the greatest or the highest restriction to the flow of gases. So at the very beginning of the intake or exhaust system, the opening is very small, so it gradually opens and comes to the fully open position and then closes up gradually. So the minimum cross-sectional area in the intake and exhaust system occurs usually at the valves. So therefore, it is very much important for us to seriously look at the flow-through valves. And with one-dimensional models, we can model them into a reasonable accuracy, assuming it's a quasi-steady compressible flow, just to understand or just to get an idea about what exactly happens in these processes, thermodynamically and in terms of fluid mechanics. So the valve timing, I'm pretty sure you all are familiar with this valve timing diagram. So usually this is intake valve, opens before the top dead center. So at the end of the exhaust stroke, before the piston reaches its top dead center, the intake valve opens. And it remains open, usually beyond the bottom dead center. That is, from this point onwards, the compression of gases occurs, but still the intake valve is open. Similarly, the exhaust valve is open somewhere in the expansion stroke before the piston reaches the bottom dead center, and the exhaust valve is usually kept open beyond the top dead center. That means the exhaust valve will remain open for some time in the intake of the next cycle. So the reasons are early intake valve opening would facilitate the gases to go out efficiently, effectively. So that is called blowdown. So we will look at gas blowdown later on. And negatively, it will affect on the expansion, because when you open the valves, exhaust valve during the expansion stroke, some of the power that can be extracted from the system will go to waste. And the late intake valve closing is usually beneficial at the high speeds. There's something called RAM effect, which would augment the induction process. But again, at low speed conditions, there will be a backflow taking place. Some of the induced gases go back to the intake system. Accordingly, the volumetric efficiency would be reduced. And also, that will negatively affect on the compression ratio, because when the valve is open, the volume would be a little more than that other volume of the cylinder, because some of the areas in the intake system also need to be considered because it is open. Now let's look at the dynamic effects in little more details using one-dimensional valve flow modeling. As I mentioned earlier, to understand exactly what happens inside an internal combustion engine, we have to do a three-dimensional computational fluid dynamic analysis, which need a lot of computational power and time. But to get a reasonable understanding with a reasonable accuracy about what exactly happening, we could use one-dimensional models. So you all know the Mach number M equals U over C fluid mechanics. U is the gas flow velocity and C is the speed of sound. And if Mach is 0, M is 0, then we know that it is a stagnated condition where there is no flow. In other words, we can create a stagnated condition by assuming all its kinetic energy flow is transformed into internal energy and the pressure volume work. Now for intake flow, the stagnated condition that we consider is a point on the intake upstream, that is somewhere in the intake system. And for exhaust flow, the stagnated condition that we consider is the condition inside the cylinder. The direction of the flow during outflow is from the cylinder to environment, and during the inflow is from the environment to the system. So the stagnated point we consider is always in the upstream. So the upstream is intake system for intake, and upstream is a point on the cylinder for the exhaust. We can say the specific enthalpy at the stagnated point equals to the specific enthalpy of the gas plus U squared over 2, which is a constant. Now we know that dH equals Cp dt from the thermodynamics fundamentals. Accordingly, we can represent this equation in terms of temperature like this. So just substitute this to this. And then we know that for ideal gas, the constant C, the speed of sound is square root of gamma RT. And universal gas constant is Cp minus Cv. And gamma, the specific heat ratio, is Cp over Cv. And the Mach number is, of course, U over C. Now, if you get rid of this Cp and U using these relationships, then you can write down the temperature ratio, temperature between a particular point on the downstream and a stagnant point in the upstream, something like this. Temperature ratio is a function of Mach number and gamma. And if the flow is isentropic, then we know that the pressure ratio equals to the temperature ratio into the power of gamma divided by gamma minus 1. Accordingly, we can replace this temperature ratio in terms of pressure ratio and write it down like this. So the pressure ratio is a function of Mach number as well as gamma. Now, if you further look at this, temperature ratio is the volume ratio into gamma minus 1 if the process is isentropic. Then the mass is rho into V, the density into V, which is a constant mass conservation. Accordingly, this volume ratio can be represented or replaced with the density ratio. So the density ratio will be the temperature ratio into 1 upon gamma minus 1. The relationship between pressure ratio and temperature ratio is this. Accordingly, the pressure ratio that we looked at earlier could be replaced by density ratio by considering this and this. Thus, we can write down the density ratio as a function of gamma and Mach number like this. If you consider a geometry like this, so this is the valve, this is upstream and this is downstream if it is intake system, and this is upstream and this is downstream for exhaust. So O represents the stagnation point, V represents the point on the valve open area. So V is in the downstream and O is on the upstream. If the process is isentropic or adiabatic, we know that PV gamma is constant. And replace the pressure volume ratio with the density ratio because it is constant. So we can write down the density ratio like this. So V is a point on the valve open area and O is the stagnation point in the upstream. V is downstream, O is upstream. Then you can consider the mass flow rate through an orifice. So this is the upstream condition, the stagnation condition, and this is the downstream condition, which is the valve throat. So the mass flow rate is density, cross-section area into the velocity. And if the flow is isentropic, then we know that at the stagnation point, all the kinetic energy is transformed into internal energy and the pressure volume work. This is the enthalpy, specific enthalpy at the valve throat, and this is the isentropic flow velocity. Isentropic flow velocity. So the isentropic square of the isentropic flow velocity will be this. Now we know that dH equals Cp dt. So we can replace this H or the specific enthalpies with Cp and T. And then if you take T naught out and replace this temperature ratio with the pressure ratio, considering the adiabatic condition, then we can write down the square of the isentropic flow velocity this way. And this can be further simplified by considering the ideal gas relationship at the stagnated point. And the universal gas constant, Cp minus Cv, and a gamma is Cp over Cv. So if you substitute these values into this to get rid of this temperature T0 and represent in terms of pressure and density, then the flow velocity or the isentropic flow velocity could be represented like this. Accordingly, the mass flow rate, we know that it is rho V, AF, and UIS. UIS, the flow through the valve, isentropic flow. AF is the valve flow area, and rho V is the density at the point of the valve. And the density ratio we have already found earlier. Thus, we can say the mass flow rate according to this relationship. Perhaps we would have obtained this relationship earlier also under fluid mechanics, that is compressible flow through orifice. So using this relationship, we'll be able to find the mass flow rate. If you know the speed of sound under stagnation condition, density of the stagnation condition, and the pressures at the stagnation condition, as well as the valve open area. The C naught is, of course, gamma, square root of gamma RT T naught. Now we know that this flow becomes choked when the pressure ratio exceeds critical pressure value. That is when M is greater than 1 or equal to 1. So the critical pressure ratio is the pressure ratio when M equals to 1. So pressure ratio, we have earlier obtained a relationship. And when M equals 1, then this becomes this equation, and that indicates that the pressure ratio under critical condition or the choked flow condition does not depend on the velocity or the Mach number. It is purely a function of the specific heat ratio. Specific heat ratio. For example, for a mixture of gamma equals 1.35, the critical pressure ratio is 1.86. When the pressure ratio goes more than 1.86 or equal, then the flow becomes choked. So the flow becomes critical. So this is what I just said during the condition. And under the choked conditions, where the pressure ratio goes to a critical condition, we can say that our critical mass flow, replacing pressure ratio with this critical pressure ratio, we can get a simplified relationship for the critical mass flow rate across the valve. And if you plot this mass flow rate across the valve against the pressure ratio between the pressure at the valve open area and the pressure at the stagnated point, which is the upstream pressure point, and the critical pressure ratio, let's say over here. And if gamma equals to 1.35, critical pressure ratio, we know that 1.86. And that is, so this is P naught over PV. And what I have taken here is PV over P naught. Accordingly, this is the reciprocal. So the value is 1/1.86, which is 0.54. And if you plot the mass flow rate at different pressure ratios, what you would see is something like this. And in this region, mass flow rate is governed by the pressure ratio. So when the pressure ratio is changed, the mass flow rate is changed. But when the pressure ratio is below this one value, the flow becomes choked. And as a result of that, mass flow rate becomes independent of the pressure ratio or the manifold pressure. So choked flow, the flow is governed by gamma, not the pressure difference.